Happy snow day! So I know we missed this entire week and we're going to piece it all together with some videos. The first one is finishing up section 5.6 from last class. And then we're going to have my friend take you through complex numbers, and then I will be back to talk about quadratics. So thank everybody for their patience, and let's continue here with example 7. On the previous pages, we were solving when we had square roots in our equations. These are called power functions because they have numbers in the exponents, and they tend to be really nice to solve. Many of you already know how to solve these, so I'm going to whip through A and B and C on your notes here. And I would suggest pausing if you need to write things down, and rewinding if you didn't catch that. That's one of the great features of video. The bad feature is that I don't make great ones, so let's get this one done. So I have x cubed equals 27. To get rid of an x cubed, I take the cube root of both sides because the cube root is the inverse of the cube. And you get this statement that x equals the cube root of 27. You can stop and ask yourself what number multiplied by itself 3 times gives you 27. And I already know you're all saying, Amy, the answer is 3. It's an x value, so you're going to give it that curly brace notation after you go back to the original equation and shove it back in. Going to the next problem, x squared equals 11. You've already solved a ton of these. Take the square root of both sides. X equals the square root of 11. And now we have to talk about why I'm putting a plus or minus here. When you take the square root of both sides of an equation, you don't know if you're taking the positive or the negative inside this particular x squared. For example, if I have x squared equals 49, how do you know I wasn't meaning negative 7 squared or positive 7 squared? Both of those particular numbers squared will give you a positive 49. Because of this plus or minus issue, you have to, when you take the square root of both sides, make sure that your answer contains both the plus and the minus part of the radical 11. You do not need to do that for anything cubed or anything with an odd power because we can have negative numbers in the odd powers. Here we are with fourth power here. You're going to take the fourth root, and when you take the fourth root, you too must put a plus or minus, because it's an even power. This 4 and this fourth root cancel each other out. And then we have to ask ourselves, what multiplied by itself 4 times gives you 81? It's 3. We're not quite done with this problem. We need to add 4 to both sides. When we add 4 to both sides, please put it in front of the plus or minus. And now you have 2 possibilities. You have 4 plus 3 and 4 minus 3. So this one here, that first answer, I'm just going to put up here, is 7. The second answer is 1. So take a look at the practice problems here. They are not in your homework. They're just extra practice. And I will have answers for these on Monday, which I hope we have school on Monday. So take a look at these, freeze the screen, write them down, practice them, because they're coming to an exam near you soon. So we're going to talk about the Pythagorean theorem because that is the last piece of 5.6 before we can move on. Many of you have heard it as a squared plus b squared equals c squared. But it's actually not. It's only for right triangles. And it's literally leg squared plus leg squared equals hypotenuse squared. And you may think I'm making a big deal, but we're going to be using a, b, and c for the quadratic formula really soon, and I don't want you confusing that a, b, and c with the a, b's, and c's using for the quadratic formula. So these are only right triangles, And here's the hypotenuse. It's always the longest side. And this is one of the legs, and here's the other leg. So we're going to run through an example or two with Pythagorean theorem. I've got the first right triangle here. Check to make sure you have a right triangle, and then you can use the Pythagorean theorem for the missing side. So this would be leg squared plus the other leg squared equals the hypotenuse squared, because this is the longest side. Here's a leg, which is t squared plus 144 equals 169. And then I'm going to subtract 144 from 169, and I think that's 25 on a good day. Then I need to take the square root of both sides. And now I have two possible answers because I've taken the square root of both sides, and I just talked about doing the plus or minus. And the square root of 25 is plus or minus 5. However, you can't have negative distance. So, one of these is extraneous, and the only answer that you have is t equals 5 because the Pythagorean theorem is measuring distance. So, this is one of those cases where you can't have negative distance or negative time, so you can't use the negative part of the plus or minus answer. Hold on while I slurp some coffee. So, now that I know how to use the Pythagorean theorem, although I'm guessing almost all of you already know how to use the Pythagorean theorem, you can use the facts of the Pythagorean theorem to check to see if you have right triangles. Because if it works, leg squared plus leg squared equals hypotenuse squared, that means you actually have a right triangle. Like if you were fishing for triangles in the triangle ocean, and you knew you pulled up a right one if it worked on the Pythagorean theorem. So let's try it. So we've got 7 squared plus 24 squared equals 25 squared. And I'm asking the question, is that true? Now, before I move on, I'd like to say the reason I put all of these numbers in the places I did was that I knew the hypotenuse had to be the longest side. So it's the one where we have leg squared plus leg squared equals the longest side. So I'm going to say, is 49 actually equal to, well, 24 squared? I'm going to give you a second to go get that number, and 25 squared, and I'll return with them here. So did you get that 24 squared was 576 and 25 squared was 625? I did, which is cool. So I still have a question mark over my equal sign because I don't know yet if this side is going to equal that side and we will have a right triangle. So I'm going to add 49 to 576, which I've done a little bit previously, and I get that the left side of this equation is 625, and that does indeed equal the right side. So, yes, you have a right triangle. Yay, you caught one. All right, so a use of the Pythagorean theorem is the distance formula, and you may have seen the distance formula before. D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Make sure that your root goes all the way across. But in this class, you need to know y. So I'm going to talk about y. I'm going to draw a beautiful Cartesian plane here. And I'm talking about the distance between 2 points. And the distance between 2 points is always going to be shortest when they're connected by a straight line. So I want to know the distance between A and B. And I'm going to remind everybody here that the distance between A and B also is going to involve x1, y1, because that's the ordered pair for spot A, and then x2, y2, because that's the ordered pair for part B. So it turns out that if I make this a right triangle, which is where Pythagorean theorem comes in, and I remind myself I'm looking for this distance d here, all I need to do is hold my pencil and find the vertical distance. We already know how to find vertical distance. It's the rise of this particular equation, or excuse me, these ordered pairs. And I find vertical distance by y values. The top here is going to be y1, the bottom here is going to be y2, And so I know that this side is going to be y2 minus y1. This should feel a little bit familiar from using these particular values for slope. So continuing my argument here, to find my horizontal distance, I know it's going to be this number here, this x2, minus this number here, x1. You could remind yourself this is just the run of this particular triangle. And Pythagorean theorem tells us that leg squared, x2 minus x1, because that's this whole leg, squared, plus the other leg squared, which is y2 minus y1, and squaring that is going to equal d squared. Well, I don't want a square of d, I want d by itself. So to get d by itself, I'm going to take the square root of both sides. When I do, I get that a single d is equal to the square root of, whoa, that went wrong really quickly, there we go. The square root of x2 minus x1 squared plus y2 minus y1 squared. The reason I don't use plus or minus is that this is truly a distance, and distance can never be negative. So now that we know the origination of the distance formula, it's just a formula that came right from Pythagorean theorem, we can do two examples. We're going to do one where you're looking at a graph and one where I'm just giving you 2 points. And so looking at the graph, the first thing that you need are the x1, y1s. So point A here is sitting on the ordered pair -2, 4. And point B is sitting on the pair 4, 2. And so you can choose either point to be point 1 or point 2. Doesn't matter. I'm going to say this is point 2 and this is point 1, but dare to be different. You're welcome to change that up if you want. So I start with d equals the square root of, and x2 in this case is 4, minus x1, which is -2. Notice my very nice use of parentheses because I'm going to have a minus minus here. That whole thing is squared. Plus y2, which is 2, minus y1, which is 4, squared. And again, I'm really only using those parentheses to remind myself to change the sign in there. So I'm going to do that first because PEMDAS says parenthesis first. So 4 minus minus 2 is 4 plus 2. Plus 2 minus 4 is -2. I'm going to go ahead and shorten that up. So I've got 4 and 2 here to get 6 squared plus -2 squared. 6 squared is 36 on a good day, and -2 squared is 4. And so you begin this process with the square root of 40. But I will remind you, we know that we can't leave it the square root of 40 because there is a perfect square hiding in the number square root of 40. So bringing it over here, the square root of 40 can be made into 4 times 10, which is now the square root of 4 times the square root of 10, which is now 2 root 10. And I would like to remind everyone at this moment, you are 100% on the hook for making sure you're not leaving your answers as unreduced radicals. Let's do this again because it was fun the first time. It'll be fun the second time. Except this time you're not going to do it on a graph. You're just going to do it with 2 points. So I'm going to hit d equals the square root of, again, choose point 1, point 2. I'm going to mix it up because I felt like I, did the very normal thing up here. So I'm going to mix this up and say this is point 2 and this is point 1. So that will be x2, which is 3, minus x1, and again, parenthesis, -4 squared, plus, and then y2 is 9, minus y1, which is the number 2, squared. That's going to equal, I'm going to do the plus here to get 3 plus 4 squared, and then I'll leave this so it's all consistent. 3 plus 4 is 7 on a good day, and 9 minus 2 is also 7. So both of these reduce down to 7 squared plus 7 squared. And that's going to equal 49 plus 49, which is going to be the square root of 98. And you're like, woot, got an answer. But we know there's a perfect square hiding in the number 98. It's here. We know that 98 is 49 times 2. You can separate that out to the square root of 49 times the square root of 2, which is 7 radical 2. And that is how you use the distance formula.